Okay. Hello, everyone. My name is Zhang Xiatian. I'm from Token Data. We are a leading big data platform in China. Today, I'm going to introduce how we make Spark support 1 trillion dimensions logistic regression. This is parameter-free and super faster. It is beyond the common sense about Spark for machine learning. At first, let us look at the current limitation of Spark for machine learning, because everyone knows the core programming diagram of Spark is MapReduce, and that brings two problems. The synchronous communication between computing nodes generate very high cost, and the model size is heavily limited by the memory size of a single node. Usually, the maximal size of the model size is no more than 100 million dimensions. But in real business case, there may be very huge dimensions. Such as more than 1 billion, even more than 1 trillion dimensions. So our goal is to tackle those real business challenges. We want to implement a logistic regression algorithm on Spark, which can be parameter-free, super faster, and most importantly, it can support a 1 trillion dimensions model. It seems like an impossible mission, but luckily we made it, and today I'm going to share our story. At first, we invented a new efficient optimization method. We call it greedy step averaging. If you are interested in our work, you can find it in the archive website. GSA is similar to classical optimization method SGD, except that the learning rate is assigned and updated automatically during the training process. As you can see here, in the general algorithm flow, the difference between GSA and SGD is on the step 4 and 5. On the step 4, GSA calculated the greedy step, which minimizes the local loss of the current training example. And the step 5 set the current learning rate by averaging current and all previously greedy steps. And here is the performance comparison between GSA and SGD. We have done a group of experiments on the two implementations of logistic regression by using 4 different data sets. As you can see, the red lines are the convergence curves of GSA logistic regression, and other colors are SGD logistic regressions with different parameter setting. Apparently, although GSA is not all the best over all the time and all the problem, but it is very stable and at least is very close to the best performance. Additionally, the SGD is very sensitive to the learning rate. Okay, we made a very solid first step, but GSA is a single process method. To handle real large-scale problems, we still need a parallelization capability with high efficiency. Today, the mainstream parallelization method is grading the averaging method, which is that collects the grading on each on computing nodes and updates the global model by averaging the local gradings. This strategy is also used by MMLib. But one great limitation of this method is its heavy communication cost between the computing nodes. That may slow down the training speed. However, another simpler parallelization method is known as model averaging. It's just train the local models over the computing nodes and simply averaging the local models as the global model. In the end, apparently, the communication cost is much lower than the grading averaging method. But one great limitation but one challenge of its method is in the traditional opinions. There's no theoretical guarantee of its method, but based on the new theoretical support and the real tester, we found finally we choose the model averaging method as our parameterization method. Here is the one paper published most recently, which we found as the theoretically support of the model averaging method. I won't go deeper into its paper today, as there is much mathematical details, but I can give you one important conclusion, that for big data problem, the model averaging method is able to approach the optimal model on linear problems. Besides theoretical support, we also did a series of performance tests to prove our thoughts. In our test, we compared the performance of our GSA plus model averaging logistic regression against the MLlib's implementation. There are 6 different datasets for test, as you can see here. And all the blue lines are all algorithms, AUC convergence curves, and the green lines are MLlib, logistic regression. If we can find out that all algorithms converge very fast with just one-time scaling of the data set, it can approach the best performance. In contrast, the MLlib era varies. The performance of MLlib logistic regression varies on different data sets. One thing to be noted here, that the comparison results of MLlib logistic regression are selected from many experiments with different parameter settings. Okay, the second step is perfectly done. The final challenge we are going to tackle is the common sense that Spark cannot support a very large size model. When we dive deeply into the model averaging method, we found that there are some interesting points. Firstly, for large-scale machine learning problems, the data sets are very sparse usually. That means the trained local models are on each data partitions is also sparse and can be stored in memory. As a result, the global model size cannot impact the local model training process. And secondly, if we put the averaged model into RDD, that's the model size is not be limited by the single node's memory limitation. The real bottleneck is in the scoring stage. average model RDD is maybe too big to collector and broadcaster. And so we should find a way to put the large scalar model into a single computing node. Then we use a simple model comparison strategy. At first, we discretize parameter values by k-means, such as discretize these values to 128 buckets. Then we can use 7 bits to encode a bucket and build a mapping index to discrete parameter values. Next, we put all the parameter value coders into a bitmap. In the end, we use rolling bitmap to compress the discretized model. And after each steps, eventually, we are able to broadcast the huge model to the different computing nodes to score the samples on the different data partitions. One major concern about a compressed model is the accuracy loss. For this, we also did a serious tester. We used 3 different data sets here. You can see in this table the loss of accuracy and the AUC is just within 1%. That is totally acceptable. And the efficiency is also very important. Let us check the efficiency of the model comparison method. We vary the model size from 20 millions to 1 trillion by crossing the features in the original data set. The original data set contains more than 500 million samples and with 20 million features. As you can see in the table, for 1 trillion dimension models, is here model we can include a compressed model, and we can finish this in 14 minutes. It is super faster. Consider the scale of the problem, and for other relative small scale problem, it's all are finished in 10 minutes. More importantly, we achieve its performance just use a very limited computing resource. For all the testers, we just claim 48 executors. For the testers, the dimensions is less than the 10 billions. We just need 1 gigabyte for each executor. Even for the 1 trillion billions problem, the requirement of the computing hardware is just about 6 PC servers with 64 gigabytes memory. Actually, we open source its work in the Fregatta project. That is a machine learning project of token data. This project is published on November 13 last year. By now, we get more than 416 stars on GitHub. Welcome to tester user comments on and even join our projects. That's all. Thanks everyone. Besides, our company also have a booth in the hall. If you have some interesting about our work or our company, can go to our booth. Thanks again.
Thank you, Zhang. All right, good stuff. Just give us a minute here. We'll be getting Jack set up. Jack from Hewlett Packard Enterprise talk about structured streaming in columnar data warehouses. Should be getting started here just in 5 minutes.
I have a quick question. So when you talk about the 1 trillion parameters, and do you put those 1 trillion parameters in some centralized storage or no?
Sorry, I didn't catch you.
You have 1 trillion parameters, right?
Yeah.
Don't you need to keep those 1 trillion parameter in memory somewhere during the training time?
Because we use the model averaging method, then we didn't need to keep the global model in the memory. Because in the map process, we just train multiple local model. That is limited. The size is very limited because of the sparsity of the data sets. And in the reduce process, we just integration all the local models into a huge global model, but it's stored in the RDD, not in the memory.
So when you have 1 trillion parameters, how much training data do you have?
What?
How many training examples do you need?
More than 500 millions.
That does not add up. 500 million training examples, 1 trillion parameters?
Yeah.
How could you work? That could not work, right? With each example, you have a lot of parameters associated with it.
What?
I just, maybe you could take offline. In order to train 1 trillion parameters, you need a significantly more training data to make those parameters make sense, no? And maybe we could take offline.
Okay.